Astrophysics, her work focused on the interaction of peculiarities, and dynamics. And today, we're going to talk about the two peculiarities of black hole interaction.
So first of all, I want to thank the organizers for setting up, and I think that so far, well, Elaine's talk was awesome. I hope mine was up to it. But what looks to be a great workshop for the rest of the day also. And thanks for inviting me. Thanks for organizing. I'm gonna. This is gonna be a somewhat of a change of gears from Elaine's talk. If there are, I think, no formulas in my slides, but also there are no pretty pictures. So you gain some, you lose some. And for those who've seen me give talks before, you know that I generally like to begin the talk with a quotation to set the mood. And I will be doing that here, but I'm actually starting to carry it to a little bit of an extreme, as you'll see. So this quotation is from one of my heroes, James Clerk Maxwell, who I think all of us in this room can agree is someone worth listening to. He says, he's giving an address as he was the president of the mathematical and physical section of the British Association in 1870. He's giving an address to the association. We are met as cultivators of mathematics and physics. In our daily work, we are led up to questions the same in kind with those of metaphysics, and we approach them not trusting to the native penetrating power of our own minds, but trained by a long continued adjustment of our modes of thought to the facts of external nature. I want you to please keep this last bit. Does that come? Wait, is there? Oh, I see. Okay, forget it. Keep this last bit of the quotation in mind throughout the talk. I will return to it at the end. Not trusting the native penetrating power of our own minds, but trained by a long. Francis Bacon, someone perhaps that we may not all agree is worth listening to, but I think he is. The subtlety of nature far exceeds the subtlety of sense and intellect, so that these fine meditations and speculations and reasonings of men are a sort of insanity, only there is no one at hand to remark it. I'm here to remark it in this talking paper. And finally, most straightforwardly, I think really requires no comment. What bizarre shit? Thomas Pynchon. This, I take it, I trust that the sense of this will be clear throughout the talk. Because we are going to be talking about black hole entropy, and that is some really, really bizarre shit, as we will see. So I'll begin just with a little bit of setting of the stage. I'll discuss why we want to posit or black hole entropy at all, why we want to attribute entropy to black holes. Possible arguments, some of the arguments that have been given, reasons why I find some of them not really adequate. I'll then discuss what kind of entropy it is that we are attributing when we do attribute an entropy to black holes. I'll spend a short amount of time talking about a feature of entropy that isn't discussed so much in the literature, of the fact that it's one of its, to me, most characteristic properties is that it has a weird modal feature to it. It's a modal quantity in a very odd way, and how that may shed some light on the properties of black hole entropy. And I'll conclude with raising a few questions that all of this has brought well, I think lead us to, but I won't have time to say much about them. It'll be more just in the spirit of raising questions that I hope other people will pick up and work on, especially all the young hotshots in the audience. So, what is black hole entropy? Well, it's A over 4. I think we can more or less all agree on that. I mean, there's more to say. There's possibly corrections of order H. We're basically done. It's all possibly true, but so far it's not very illuminating. Last quotation, person. One who offers clarity in facts but not illumination is insufferable. So I've offered you so far, I think, clarity and facts, but I hope now to give you some illumination, or at least to try and spell out where I think illumination is needed. So why black hole entropy at all? Why do we want to attribute entropy to black holes in the first place, besides the formal analogies between the laws of ordinary thermodynamics and the laws of black hole mechanics in the classical case, or black hole thermodynamics in the semi-classical regime? I think everyone more or less agrees that the formal analogy by itself doesn't suffice for attributing real physical significance to the claim that the area of a black hole is or is proportional to an entropy for the black hole. And I mean, standard black holes at the horizon are vacuum. It's just it's a region of empty space-time that is not locally is completely undistinguished. If you're passing through an event horizon, you can't tell that locally. How on earth can it have a property like entropy, which manifestly seems to be essentially associated with matter, stuff, with the coffee in my cup? How can the entropy of the coffee in my cup be at all, not even same, but in any way similar to the area of a black hole? Well, perhaps the most initially plausible way to explain what black hole entropy measures and why black holes may have such a property in the first place is to point to Hawking radiation. We actually have a derivation of Hawking radiation. We have many derivations of Hawking radiation, in fact. And the fact that Hawking radiation has a well-defined temperature that it seems to stand in an appropriate relation to the area of the black hole by the first law of black hole mechanics seems to suggest, well, we should then think of the area as an entropy, because temperature and entropy, they go together like first and second. Or actually, I think more like sperm and draw. But they go together, is the idea. Well, not so fast. I actually think that there's no real connection between Hawking radiation, Hawking temperature, and black hole entropy. At least not any connection of the kind that would give an argument in favor of attributing an entropy to the black hole in the first place. If you already have reason to think that the black hole has an entropy, then the connection to Hawking radiation is significant. But first of all, there are some kinds of entropy that are defined for systems without a temperature, Shannon entropy. And
before Hawking wrote his paper, Bekenstein already gave the answer. No, you lower a box of gas into the black hole horizon and so on.
Well, unfortunately, a few things to say about that. One, the example you just gave of lowering the box to the black hole is actually Grouch's counterexample of attributing entropy to the black hole. Bekenstein had to figure out a way around that. And all of Bekenstein's arguments are information theoretic, which is crucial for which is crucial at the time, because Bekenstein didn't have anything else to base his arguments on. Bekenstein's original arguments are fascinating because in some ways they're really crappy arguments, but that's not to criticize them, because pioneer work is hard. If you're the first one making an argument in a particular field, and it's really quite a revolutionary idea, your argument probably is not going to be watertight, but it's still an extraordinary idea. So I think it wasn't accidental that, as far as I can tell, both from talking with people like Wald and Unruh, who were there at the time, and with looking at the literature, no one believed Bekenstein except possibly John Wheeler. And John Wheeler was batshit crazy. I never thought Wheeler was batshit crazy anyway, so no one took that. No one took Wheeler's endorsement very seriously. No one believed Bekenstein until Hawking radiation. It was only with Hawking's derivation that people said, this real. Actually, Bekenstein was right. This really isn't it. So but having said that, as you'll see in a few slides, I actually think that Bekenstein's original motivations is still the best one, just to give you a preview. So some kinds of entropy are defined entirely independent of temperature, but most importantly, Hawking radiation, there's a sense in which the Hawking mechanism is entirely a kinematical effect. you really need only, speaking roughly, you basically need a Lorentz metric and you need an appropriate affine structure. And you need basically the property of quantum field vacuum in Ferg space-time that different observers will see different vacua. And that's all you need. And you will automatically get a Hawking effect. You'll automatically get a scattering with an appropriate long spectrum. And it has nothing to do with dynamics. It's completely independent of the Einstein field equation. That's not true for entropy, for black hole entropy. The fact that we define the black hole entropy as A/4 depends sensitively on the Einstein field equation. So I don't think that invoking Hawking radiation can give us any argument to support the attribution of entropy to black hole. So then there are people will say, but quantum gravity calculations, they give us A/4. That's why we should think about that. That's why we should attribute, an entropy to the black hole. So I don't think that this can work either. I'm not going to give you the arguments why I don't think that this can work here. I will give you the arguments for this in the next section when I'm talking about a related issue. So hold that thought in abeyance for a few minutes. I actually think that Bekenstein's original motivation to save the second law seems to me the best argument, because it was in the late 60s, Wheeler apparently was walking around, the Palmer laboratory, grabbing people in the hallways and saying, "What happens to the second law when you throw a cup of tea into the black hole? This highly entropic object, you're spontaneously lowering the entropy of a causally isolated system, the outside of the black hole." And that seems to be a violation of the second law. So, does the second law not hold when there are black holes around? Well, this was Bekenstein's motivation for attributing entropy to the black hole. And I think that this is still, in fact, the best motivation, because one of the truly remarkable facts about the second law is that no matter how deep we go into physics, no matter how far the regimes we probe and the regimes we study are from our everyday experience, we always find entropic quantities that satisfy a second law. This seems to be one of the few truly universal features of physics. So if anything is if we want to hold on to anything when we're thinking about regimes that we don't have direct experimental access to, or even indirect experimental access to, but we need some kind of ideas to guide our theorizing, it seems to me very plausible that holding on to the second law is a good place to start. But a real defense of this claim is another talk entirely, and so I'm not going to go into it. So what kind of entropy are we talking about when we attribute an entropy to the black hole? So there's a lot of options to choose from. It can be a thermodynamic entropy, phenomenological or Clausius. It can be a Boltzmann entropy. It can be Gibbs entropy. It can be a von Neumann entanglement entropy. It can be Shannon information entropy. It can be holographic entropy. It can be something else entirely. There are various more exotic proposals for what one might mean by entropy in these contexts. So what of the various options are best, appropriate, consistent, possible for a black hole entropy? Because these are not, even though as a physicist, as a practicing workaday physicist, we would never really distinguish between, say, Boltzmann and Gibbs, and there's good reason for them not to. Conceptually, they are radically different. And if we're worried about foundational issues, we do need to keep track of the difference. So attributing a thermodynamic entropy to the black hole. I think that no matter what else is the case, we'd better be able to do this. There better be a good thermodynamical conception of entropy for a black hole. Because without a justification and understanding of a black hole as a thermodynamical system in the sense of phenomenological gross thermodynamics, without invoking statistical mechanics to start with, at least, we have no real evidence in the first place that black holes even should have an appropriate statistical mechanics. Because all of the evidence we have that systems have statistical mechanics is that they obey gross thermodynamical properties. If you look at what StatMech people do in laboratories, they almost all the measurements they make, almost all the kinds of systems they study are really measurements of thermodynamic quantities, and then they do calculations to extract the statistical mechanics, fluctuations and such. That's starting to change in the laboratory. We're actually now getting to the point where we can really get a grip on the fluctuations themselves. But for the most part, it's still the case. Most of our evidence for StatMech and StatMech properties comes from measurements of thermodynamic properties. If we don't have a grip on understanding these things as thermodynamical systems, I think we don't have real good justification, especially for systems that we can't probe, like semi-classical black holes. We don't have good justification for thinking that they have an underlying statistical mechanics in the first place. Quantum gravity programs can count all the microstates they want, but we need independent reason to believe that they're counting the physically relevant microstates. And this is the first part of my argument for why quantum gravity calculations can't justify an attribution of entropy to black holes. Even if they define an appropriate class of microstates in their framework, they construct some counting argument. They say this is the form of entropy in my statistical mechanics as I am going to define it in my framework. And it turns out that this counting that I do, that I claim is supposed to return the entropy, gives me approximately A/4 with corrections of the order of h bar. That can't be evidence that A/4 is an entropy until you have given me independent reason to think that both the states that are being counted and the way they're being counted are dynamically relevant in the sense that they are the appropriate dynamic, appropriate dynamics and states to give rise to a thermodynamical entropy. And I'll say a bit more about that, what I mean by that, in a moment when I give you the second part of the argument against why I think quantum gravity calculations can't give support for the attribution of entropy to black holes. So in favor of the thermodynamical entropy, of attributing a thermodynamical entropy to black holes, I think the best arguments are the generalized second law itself, that the fact that we have various proofs in the sense of physics math, generally not in the sense of real math, but but we're doing physics, we're not doing math. So Pache, Mullany, where she that in this area we unfortunately almost never get the rigor that we would like. So, but in physics math we have a lot of proofs of the GSL, and those proofs almost for the most part give you reason to think that the kind of entropy that's being used has an appropriately thermodynamical character. Semi-classical black holes support the construction of Carnot-like cycles, so that seems to be some evidence in favor of attributing a thermodynamical entropy to them. And then there are some really speculative, one might say crazy arguments that in fact classical black holes and strictly classical matter jointly have a well-defined thermodynamics, and so the area of the black hole actually acts as a thermodynamical entropy. And that's an argument that a few folks like, including from time to time the person who wrote the paper, but not always. I think there are plenty of grounds for questioning and criticizing these two as reasons to attribute a thermodynamical entropy to black holes. I think the first one is really very strong. But we want statistical mechanics still. But classical GR by itself, and nor even semi-classical gravity can provide a statistical construction, because black holes in semi-classical gravity are still treated classically. In the framework of semi-classical gravity, a black hole is defined using the space-time geometry of a classical space-time, of a Lorentzian geometry out of four manifold. So there's no way to describe in this context, in the semi-classical framework, a black hole by physical attributes arising as gross statistical measures, over underlying or finely grained statistical quantities. And any statistical accounting, therefore, must come from a theory that is, in some sense, more fundamental than the classical space-time description, and that attributes that posits microstructure and some kind of coarse graining that, in an appropriate sense, gives rise to classical space-time geometry in some kind of thermodynamical limit, or in some. I shouldn't bias the question. It doesn't have to be a thermodynamical limit, but it has to be some kind of appropriate limiting procedure where we get from underlying non-classical microstructure to classical space-time geometry. And this underlying microstructures will presumably be quantum in nature because everything else is quantum at small scale. So why not space-time geometry too? So in favor of attributing a Boltzmann entropy, a surprisingly common argument originated with Sorkin back in the early 80s. And I can actually sketch this for you very quickly because it's an incredibly ingenious and elegant argument. So the claim that Sorkin made is that the Planck length plus the fact that black holes have a distinguished geometry provide a natural coarse graining. You just cover the event horizon with Planck area tiles. The horizon then carries some kind of information, the density approximately 1 bit per unit area per Planck size tile. The total number of configurations is of the order n to 2 to the 2 raised to the power of the area, and that gives you an entropy that is area times log 2. Basically, you're really, really close to 1/4. You're done. We have a Boltzmann entropy for the black hole. So the virtues of this argument is that there are absolutely minimal physical assumptions. It's largely independent of the details of any program of quantum gravity. But I still think it's actually a pretty crappy argument. Most crudely, you're attributing bits to Planck tiles. What's the yes/no question? A bit is a 0 or 1. You have to be able to, and I'm being a bit glib and facetious by asking what's the yes/no question, because really what Sorkin needs is that the degrees of freedom that can be localized into a Planck tile are they don't have to have 2 possible values and only 2 possible values, but they have to have some finite number of values that are uniformly bounded, that are some fairly small number of possible values per Planck tile. That's so the small number being uniformly bounded over the entire sphere. And it has to be pretty close to 2 to get this to work at all. Why? Why should we think that the world has that microstructure? And in any event, I mean, so you're either not counting microstrates that are relevant to the dynamics in any straightforward and appropriate way, or else you're making this rather strong and unwarranted assumption about what the degrees of freedom that this microstructure look like or have to be. And even if you feel in some way warranted, or you make an argument that in fact we can impose this uniform bound on the possible number of values for degrees of freedom on these Planck tiles, you're making a really even stronger and I think even less warranted assumption that those degrees of freedom couple in the right way, physically couple in the right way to, if you like, the higher level, more macro degrees of freedom of ordinary matter. These degrees, if these are the degrees of freedom on the horizon of the black hole, these are the degrees of freedom presumably that are in some sense give rise to at least some part of space-time geometry. But what they actually have to give rise to get black hole thermodynamics right is the affine structure, because it's the affine structure that gives you the Hawking effect. So you have to be able to show not only that little Planck tiles have the small number of degrees of possible values for the degrees of freedom, but that those are the degrees of freedom that give rise to something relevantly at least related to the classical affine structure of space-time. I don't know of any possible argument for that to work. And that, by the way, is the second reason why I think that state counting and quantum gravity cannot give you an argument in favor of attributing entropy to a black hole, because you not only have to show that the microstates in the quantum gravity program are in some important sense dynamically relevant, you also have to show that they give rise in the way that they couple in some appropriate limit to the degrees of freedom of ordinary matter, that they give rise to the affine coupling, the coupling of the matter to the affine structure in the sense that gives you the Hawking effect.
I've got a dumb question, like,
No,
what's the connection between the area and the Planck scale area and free space volume?
very, very, very little, because you can have essentially anything inside you want. You can stick an FLRW space-time inside the horizon.
So why is it a Boltzmann entropy?
Just because you're doing a Boltzmann-like counting of microstates. Hey, I'm not defending this program. I'm just telling you what people say.
Oh, you're not there, so I can figure it out.
So I basically, in fact, already said what's on this slide, that the Boltzmannian state counting arguments and weak quantum gravity regime calculations, Straumander, Dwappa, Ravelli, Dew and Sorkin, they beg the question. They're assuming that they're counting the dynamically relevant states. They're assuming that they're doing so in such a way that these degrees of freedom couple in the appropriate way to ordinary gross matter, and that counting measure, which is what they almost always use, is the appropriate measure to use. But that is also a problematic assumption, because counting measure is almost never the right measure to use in statistical mechanics. So why should we be using counting measure here? Gibbs. I actually know of no arguments for or against Gibbs in the literature, which is really weird, because almost every single proof of the GSL actually uses Gibbs entropy. So, I do in fact think that if we want to attribute a physical mechanical entropy to black holes, Gibbs seems to me the most promising way to go. First, because all proofs use it. In fact, I know of only one proof in the literature that doesn't use Gibbs, and it's a 2D string theory, so I'm just not impressed. But everything else uses Gibbs. But the reason I like Gibbs here is because the Gibbsian statistical mechanics is exactly what you want when you have no secure knowledge of any fine details of the microstructure and the microdynamics. All you know is that the system couples thermally to external, probably coarse-grained environments. You completely avoid Boltzmannian worries about latching onto the right physical microdegrees of freedom. So I think that Gibbs probably is probably the most appropriate one to be using, just for epistemic reasons, at least, if we want to think about these issues. Now, entanglement entropy, Sorkin also, right around the same time he first gave this Boltzmann tile counting argument, he also proposed that black hole entropy is perhaps entanglement entropy. The black hole entropy is proportional to an accounting of cross-horizon quantum field entanglement correlation. Now, the virtues of this proposal, and this is, I think, a very powerful virtue, is that it supports the derivation of the semi-classical Einstein field equation, Jacobson's very, very beautiful argument. The demerits are, one, the species problem, and I've never seen any good answer to that. The species problem is essentially that as your number of species of particle grows, the entanglement entropy grows. So how can you be sure that we have the right number of species of particles to give you an entanglement entropy proportional to the area, and in particular to the area divided by 4, rather than something else? If I just double the number of possible particles, I've changed the proportionality factor for A. So I don't know of any good answer to the species problem. People just generally ignored it. I don't see how entanglement entropy can really explain the increase in entropy when a classical entropic object like Wheeler's cup T, crosses the event horizon. How can we possibly guarantee that that the entanglement entropy is sensitive to the mass of the cup of tea and only to the mass of the cup of tea at the macroscopic scale. I see absolutely no reason why that should be true. And why the entanglement entropy should show up in particular at the classical level in the area theorem, which remember is just a theorem of pure differential geometry, really. And then we give it a physical interpretation by giving the traditional standard physical interpretations to the geometric structures in the differential geometry. I mean, it may be the case, and it sounds plausible to me, and in fact, there are very good arguments in favor of the fact that as area increases, then entanglement entropy increases. But I don't know of any argument that really works for the contrary. I'm sorry, for the converse, which is that as entanglement entropy increases, area increases. But that's the direction you really need. And in any event, entanglement itself has really deep and unresolved conceptual problems that I think would need to be really tackled and addressed head on if we want to say entanglement entropy is the right entropy to attribute black holes to. That is not a reason, and Ehrman has a really wonderful paper on this. This last point is not a reason to reject entanglement entropy as the right entropy for black holes. It's merely to remark that if we do want to go this route, we have a lot of promissory notes we will be inheriting a lot of promissory notes that need to be, what's the right word? Promissory note? Redeemed. I lose words sometimes. So holographic entropy. This is the idea that the area of a privileged Euler space-like surface in the bulk proportional to the von Neumann entropy of a I'm being very crude and sketching with a very, very broad brush here, just because of the constraints of the time constraints of this talk. And I don't want to go into too many technical details, but crudely speaking, entanglement entropy, holographic entropy is the idea is that the area of some geometrically privileged Euler space-like surface in the bulk is proportional to the von Neumann entropy of a conformal field theory on the boundary. There are really very deep and interesting papers about this idea of trying to argue in favor of it and using it to argue in favor of other really deep and important ideas. I mean, the virtues, it's cool and exciting. The demerits, the only really potentially comparing derivations I know of are in really wildly non-physical space-times. There's no good reason to think, and in fact, there are reasons to think that there are no good derivations of physically relevant spacetimes considered. And holography, I think, has even less epistemic warrant, and we lack even more epistemic control over it than we do for most things in semi-classical gravity, and that's saying quite a lot. So even if holographic entropy turns out to be the right way to go, once again, you're inheriting a lot of promissory notes that need to be redeemed. And I'm not going to talk about them, but just to mention them in case you're curious, want to go do some more reading on your own. There's a fairly large class of exotica that people have, some small but vocal minorities have championed for different kinds of entropy that might be the right kind of entropy to attribute to black holes. Some of them get really crazy. What bizarre shit, really. But I'm just mentioning them in case you want to go look. I'm not going to talk about them. So let's talk a bit about the peculiar modality of standard entropy and how this bears in the possible understanding of what black hole is. Well, entropy is weird. It really is the weirdest physical quantity I know of in the entirety of physics. It has so many properties, so many attributes that no other physical quantity I know of has. I mean, first of all, it's universal in a way that almost nothing else except energy is. Almost every physical theory defines, or at least admits, the possibility of defining entropy, with the possible exception maybe of the Newtonian mechanics of rigid bodies, and quite interestingly, the Newtonian gravitational theory. But otherwise, you can define entropy for everything. And in every single case, I claim entropy is fundamentally modal, and I'll tell you what I mean by that in a moment. And I think that coming to grips with that really has the possibility to either make several traditional and rather intractable problems that are related to entropy and second law. Either it may, in fact, deepen our understanding of it, or it might make the problems even more intractable. It's not clear to me yet which way it may go. So what I mean when I say entropy is modal, it may be that the definition derives from a principle that is itself modal in character, phenomenological entropy as derived from the Clausius and Kelvin postulates. Oh, by the way, so for people in the audience who don't know really what I mean when I say it's modal, some of the physicists, I hope that most of the philosophers know what I mean. To say that something is modal means that it has to do with possibility, necessity, or impossibility. It has to do with something like counterfactuals, with considering what is not actual. Very crudely speaking. So first, the definition derives from a principle that is itself modal in character, or the quantity is not an intrinsic property of a single state, but it's rather a counterfactual measure of how states would change were it transformed into a standard fiducial reference state, Clausius entropy. Or the quantity is not an intrinsic property of a single state, but a property of a modally characterized class of states, the counterfactually possible microstates that the macrostate correspond to, also entropy. Or the quantity is not an intrinsic property of a single system, but is a property of a modally characterized class of systems, Gibbs entropy. Or it's not a quantity at all, but it's a measure or a constraint on various kinds of possibilities. For instance, constraints on dynamically possible transitions between states, or constraints on possible states a system may be in other than its actual one, or a constraint on possible ways a system may be distinguished from, interact with, or otherwise be qualified or constrained by its environment. And von Neumann entropy exemplifies, in fact, all of this. I don't understand, by the way, the relations between these, if there are in fact any relations among the conditions. I would really like to know, I really like to understand that, I don't. Intimately related to the fact that entropy has this essentially modal character is that entropy is the only physical quantity I know of, again, that mediates no physical coupling between physical systems. There's no such thing as an entropometer. There's no instrument that directly measures entropy, the way there are instruments that directly measure velocity or kinetic energy or temperature or frequency of a monochromatic ray of light. And again, this is exemplified by the von Neumann entropy. The von Neumann entropy is not a quantity associated with the system, at least on any standard understanding of quantum mechanics. Because quantities associated with the system are self-adjoint operators, and the entropy is not a self-adjoint operator. So for semi-classical black holes, though, interestingly enough, this seems to be a non-modal quantity. It's A/4. It's an intrinsic property of a single state of an individual system. No arguments are needed for a natural zero point. It has a natural zero point. The mass equals 0 for Schwarzschild black holes. Area equals 0. There's no counterfactuals involved. This is not probabilistic. The physical significance is fixed by non-modal principles, the first law, the area law, the generalized second law. So it really seems like black hole entropy, unlike every other entropy I know, is not modal, which is really weird. And there is in fact an entropometer. You get a bunch of people together who can measure little bits of area, and you send them all off and have them all measure different parts of the event horizon and let them later on get back together and compare their measurements, and you get a direct measurement of the area of the black hole. I don't really know what to say about this. Why black hole entropy seems to be so radically different from the ordinary, from all the other entropies I know of. But on the plus side, perhaps this is telling us something about, this is placing some constraint on what the possible underlying statistical mechanics might look like for black hole entropy. What a possible statistical mechanics underpinning all black hole thermodynamics may look like. Or that's, I think, on the optimistic side. On the pessimistic side, this perhaps is reason to think area really can't be an entropy. Not clear to me. So I think I've been speaking, I think, for 40 minutes. Is that right? So I'll go for another like 5 minutes. So there are many, many questions that, at least in my mind, more or less arise almost immediately based on everything I've said so far and on a few other issues I haven't directly mentioned but are immediately relevant. The ones I'm going to briefly address and make a start at addressing are the first three. There are many different entropies. How do they relate to each other? Must we in fact pick one as the one and true black hole entropy? I am a jealous entropy. I allow no other entropies to be, worshipped besides me. Do we need that, or can we in fact allow more than one entropy to be attributed to a black hole? That sounds pretty reasonable to me to talk about. How to interpret the identity claims of a black hole entropy and ordinary entropy? These are the same physical quantity. They're identical. As Wald likes to say, the laws of black hole thermodynamics simply are the laws of ordinary thermodynamics extended so as to cover a new species of physical systems. And lastly, the disanalogies of the ordinary entropy. The fact that black hole entropy doesn't seem to have this modal character is only one disanalogy. I'll discuss a few more. Is it a virtue or a demerit? And then I'm not going to go and read all the other issues, just a sampling of many, many other issues that I think are really interesting and should be thought about. But I don't have time to discuss them in this talk. If you're interested in the first one, what may this all say about the nature of space, time, and matter and interrelations, then come back in January for my talk on dark energy, where I will be talking on exactly that issue. So there are many entropy-like quantities one can associate, with a black hole in many different contexts, under many different representations, depending, among many other things, on the choice of the type of entropy, on what horizon or surface you want to associate or associate the entropy with or attribute it to, what further space-time structure you either need to assume or assume it without needing it, but just because it makes life easy in some way. For instance, the various forms of asymptotics, various kinds of symmetries, constraints on topology of various regions of the space-time manifold. You have to decide what dynamical regime you want to be in: stationary, quasi-stationary, quasi-steady, adiabatic. You have to decide what the relationship between an attribution of energy is to energy conditions, quantum energy inequalities, entropy bounds. So it's not the issue isn't only what type of entropy to use, but also exactly what the contexts are in which it is possible, or even better, reasonable, to attribute entropies to space-time structures. So do we need, is there an a priori reason to think that exactly one of all the many possibilities that people have considered, some combination of all these things, is the one and true black hole entropy? Or are we rather latching on the different, albeit similar things, which may in classical context be identified, but perhaps come apart in a semi-classical regime? And the fact that they come apart in a semi-classical regime is not necessarily a problem, because a lot of classical concepts fall apart in semi-classical and non-classical regimes. And that teaches us something about the concept of issue. So that it could be a virtue, but it may be a demerit. I'm not going to argue one way or the other. Raise the issue, what you all think about. And this is made all the more poignant by the fact that everyone and their mother formulates GSL using different types of entropy for respectively the black holes and matter. Like, I mean, when you see formulation, when they bother to specify at all what they're talking about. So it's incredibly common for someone to give a formulation of the generalized second law. And you slowly have to figure out and work out based on what they say and how they treat the quantities, that the black hole entropy is being treated, say, as a Clausius entropy, but the matter entropy is being treated as a Boltzmann entropy. Can these things be meaningfully added? It's not clear to me, maybe. But the fact that formulations of the generalized second law and the way people throw it around without really being very careful and precise about it, I think really makes this issue even more important to get a grip on. So how can a physical quantity with properties prima facie different from ordinary entropy, a spatial area, be identical with? What is the criterion for and the meaning of this identity claim? Well, I mean, it really does depend quite sensitively, to start with, on one's views on intertheoretic relations in general. There's a lot to say about that. I don't have time to go into it. I tentatively favor, as a criterion, do the two properties play the same roles in formulating analogous general principles and in characterizing the interactions between analogous physical systems? But that's only a tentative proposal. And it has, again, as almost everything in the field does, where we are completely unconstrained by empirical data. Purely theoretical and conceptual arguments tend to have, if they're plausible at all, tend to have both a lot of virtues and a lot of merit. The disanalogies between black hole entropy and ordinary entropy. So black hole entropy is not modal. It scales with the square of the mass for asymptotically flat black hole solutions, not linearly with the mass. It's even worse in ADS. Isentropic does not imply reversible. There are no Clausius and Kelvin postulates. Every other kind of physical system I know of, it's possible to decrease entropy by throwing in mass energy if you arrange it carefully. Not possible for black holes. Yeah, there seems no way, in fact, to decrease the entropy of one black hole while increasing that of another when they interact in a joint system. When they interact as a joint system, rather, I'm sorry. There's no way to split and recombine a black hole isentropically at the macro level, at anything like a macro level. So there are a lot of ways in which black hole entropy differs dramatically from the entropy of ordinary matter. And again, I think one can take this as a virtue or a demerit, depending on the virtue is this places possible constraints on what a good underlying statistical mechanics can be. We look at the differences and we kind of work our way backwards to work out what a good statistical mechanics is for it. This is exactly what Planck did in 1900. That he knew that the entropy of black body radiation behaved in some ways that were different from the entropy of liquids, gases, and solids. And he used those differences to work backwards to an appropriate, turned out non-classical statistical mechanics that was the appropriate statistical mechanics. So one might hope that we can do the same thing here. The possible demerits are, well, it's just too different. We shouldn't be thinking of this as an entropy at all. So, I mean, I can't help remarking though that at least some of these problems are possibly directly mitigated. So for the identity problem and the modality problem, we might want to say, look, the area is not identical with the entropy. The area is simply proportional to the entropy. Just like, we have a hunk of copper, then the volume is a good proxy for its entropy. Copper under standard conditions, I can just go look up some standard tables what the proportionality is between the volume and the entropy. And same thing with black holes. And then you might want to say, this also fixes the modality problem, because in order to do this, I am assuming that there really is some microstructure, that there's some statistical accounting going on that gives rise to the proportionality between entropy and area, and so it really is modal. But again, I think I think that, as always here, it's a double-edged sword. You can either take this kind of argument as evidence that black holes must have a statistical underpinning, or you can take it as begging the question. So to conclude, can these analogies teach us something about the form of the possible statistical mechanics to ground entropy, or militate against interpreting A/4 as a physical entropy? I've already said all this. So, in the interest of time, I want to conclude by recalling the epigraph from Maxwell. Everything I've said in this talk is exactly not what Maxwell enjoins us to do when we approach questions the same in character as those of metaphysics. We are exactly not trusting to the penetrating power of our own minds, but trained by a long continued adjustment of our modes of thought, the facts of external nature, because our minds have not been trained by external nature for studying these phenomena, because we've never been able to experiment on them and probe them and get empirical data that constrains how we ought to think about them. So everything I've said about black hole entropy needs to be taken with this very, very, very powerful and strong caveat. And in fact, everything in the entire field of black hole thermodynamics needs to be taken with this very, very strong caveat. Thank you.
The problem with the equation dq is TdS.
No, I think it's great.
Because you can throw things in, we can get things out. So, do you rely on that equation or not?
When I'm thinking about black hole entropy, you mean?
Yes,
I would like to rely on it, but I'm not sure what the Q is the problem.
that's just the mass of the black hole.
So,
What's going to be?
well, I mean, at least in ordinary thermodynamics, Q is not the totality of energy. You have the possibility of doing work. So, and you can.
The black hole can be created and can disappear. So the dispectral state is there. So as soon as dq is not equal to so TdS, then you have a problem.
Well, so you're saying that this doesn't work for Kerr, because with Kerr you have the spinning term that you can think of as being analogous to the angular work term for spinning ordinary bodies in classical thermodynamics.
Suppose we limit ourselves to non-rotating or non-charged. We get whole neutral matter in without angular momentum, we get the radiation out without any difference in directions. And there this equation should hold. That gives you an entity.
So I think that in that very special case, and I think it has to be, in fact, probably not only not charged and not spinning, but also asymptotically flat. I think that probably will hold. I mean, and I think that one can make sense of it, but that's a very special case. Although in this very special case, also, I think one can give reasonable arguments based on exactly what the kind of thing you're talking about, that you do get something like a Clausius and a Kelvin postulate, which I think is really important to have if you really want to be thinking about thermodynamics. So I like that. But I would still want to know how to extend it to at least the spinning case, because when we look at M87 and Sag A star, we're looking at spinning black holes.
Then, like a rare thermodynamics, you have more terms in that equation. If there is nothing more to talk about, it's not rotating, not spinning, not charged, not any of the other properties you can think of.
I will have to think about it some more. Thank you for the question.
Right. In response to, for instance, your identity claim worries, do you think some functionalism about black hole entropy would make you less worried, or do you think that it's just a philosophical position that it's too empty, too vague, to do any work here, because the functional role is just filling way too many things?
Yeah, you basically said what my problem is with it. I think you really have all the work is going to be done by filling in the details. And some people have told me that my proposal, that it plays the analogous role in formulating general principles and plays the analogous role in mediating interactions between analogous systems is a functional account. And I mean, I have no objection to people using those words if they want, calling it whatever they like, but it doesn't seem to add anything very interesting to the work that those claims are trying to do. Thank you.
In connection with entanglement entropy, you mentioned the puzzle that it depends only on the mass. And do you find that with other definitions of entropy more or less intuitive? Or would that qualify as bizarre shit in your?
It's all bizarre shit. No, I mean, at least with other the other entropies are so kind of ambiguous with regard to how to fill in the details. A Boltzmann entropy says count, give an appropriate way to count appropriate microstates. Well, that leaves a lot of details open. So I can at least, it at least is plausible to me that those details can be filled in such a way that it keeps track of mass and only mass at the macro scale. But entanglement entropy, you're telling me exactly what the entropy is. There's no wiggle room. And it really seems, it's really hard for me at least to see how that keeps track of mass and only mass.
So that's the worst case.
It seems like it to me for that problem.
Thank you for the talk. And I was a little surprised you mentioned the wall-of-error entropy. So I wanted to hear your opinion about that. Of course, it's not directly related to the counting of microstates that you're more interested in. And also kind of a related thing, you said the AQFT doesn't have a lot, but there's actually a lot of work recently on relative entropy.
Yeah, so in fact, the reason why the slide count goes up to 53 is because I had a bunch of slides at the end that have something to say about each one of those questions that I didn't address. And in the slide on AQFT, I mentioned the very recent work on relative entropy. But so thank you for that, though. That is important to point out. But it's still the case that none of that is about the GSL in particular, and none of it is about anything like the Bekenstein entropy in particular. So it's still the case that it seems like AQFT, it still is weird to me that AQFT doesn't, it seems, so far as I know, it doesn't have anything to say directly about Bekenstein. But but with regard to the first question, that was actually just a completely brain dead, stupid omission on my part not to mention, at least in the list, the wall-of-error entropy. I mean, especially, Wall was my advisor, so it's especially bad that I didn't mention it, but it was just a completely brain dead, stupid oversight. Because I actually do have things to say about it. I can tell you if you like. It would take me a little bit of time to tell you, so I won't do it right now.
There's time. It's just a follow-up to the entanglement entropy. Because you said it, you want it to be mass and only mass. But why
At the macro level.
Why the only though?
Because the entropy, the area of the black hole is proportional to the irreducible mass, and so it will proportional to the square of the irreducible.
But entanglement entropy could be giving you a more general notion of entropy, like apply to cosmology, cosmological horizons or something.
Well, that may be, but it still is incumbent upon people who champion entanglement entropy to say why, in this particular case, it's sensitive to the mass and the surface.